Ever wonder what's really inside the AI chips that are changing our world? Well, a key ingredient is something called high bandwidth memory, or HBM. And today, we're going to pull back the curtain on the incredible 12-step journey that transforms a flat piece of silicon into a multi-layered memory powerhouse.
So let's get right into it. For years and years, the way to make chips faster was to just make them wider, sprawl them out. But HBM completely flips that idea on its head. Forget the single-story ranch house. We're talking about building a skyscraper. By stacking memory chips vertically, you get something that's way faster, more power efficient, and takes up a whole lot less space. Okay, so if you're building a skyscraper, you need elevators, right? How else do you get between floors? In the world of HBM, those elevators are called through-silicon vias, or TSVs. They are these microscopic vertical tunnels that let data just zip between all the stacked layers. This is the secret sauce that gives HBM its mind-blowing speed. And that really brings us to the big question, doesn't it? It's one thing to talk about memory skyscrapers, but it's another thing to actually build them when each floor is thousands of times thinner than a human hair. The level of precision is just staggering. So how on earth do they do it? Well, we can break this whole amazing journey down into 3 main phases. First, we'll see how they drill the elevator shafts. Then, we'll look at how they get each floor ready for construction. And finally, the really cool part, assembling the whole skyscraper. Let's dive in. Okay, phase 1, drilling paths in silicon. Everything starts with a perfectly clean, simple silicon wafer. And the very first job is to lay the foundation for those data elevators we talked about, the TSVs. This is the bedrock of the entire chip. This whole phase is like a really precise 4-step dance. First, you etch these incredibly deep, narrow trenches into the silicon. Then you fill those trenches up with copper, which is an amazing conductor for data. After that, you have to polish the entire surface until it's perfectly flat. Any extra copper has gotta go. And finally, you lay down a network of wiring on the surface to connect everything together. All right, phase 2, preparing both sides. So now we've got a wafer with all this cool stuff on one side. But remember, we're building a skyscraper. Each floor needs to connect to the floor below it and the floor above it. That means we need connection points on both the top and the bottom.
And that's the tricky part, isn't it? We've only been working on one side of this wafer. To get it ready for stacking, we have to perform some serious engineering acrobatics to get to the other side. So the first thing they do is add these tiny, tiny little solder bumps to the front side, the side we've already been working on. You can think of these as the little connector pegs. Then they heat them up in a process called reflow, which melts them just enough to form these perfect little spheres. That ensures we get a super solid connection later on. Okay, but here's a massive problem. Remember those copper elevators we built? Right now, they're buried deep inside the silicon. To expose them on the backside, the wafer has to be ground down until it's unbelievably thin. So how do you do that without the whole thing just shattering into a million pieces? The solution is it's brilliant. You temporarily glue the wafer you're working on to a sturdy, supportive carrier wafer. It's like putting a splint on a bone before you operate. This carrier holds everything perfectly rigid, so you can safely grind down the back without it breaking. And this back grinding process is critical. It doesn't just expose the TSVs, it makes the final chip thinner, which means it uses less power and gets rid of heat way, way better. So with that carrier wafer holding everything steady, the back gets ground down and pop, out come the copper tips of our TSV elevators. It's pretty awesome. Then they add a protective layer and a second set of solder bumps for the backside connections. Once that's all done, the carrier wafer is gently removed, and just like that, you've got a double-sided chip ready for stacking. And now for the grand finale, phase 3, stacking the chips. We have created our individual floors. Now it's time to slice the wafer up into individual chips and assemble our skyscraper, layer by painstaking layer. So how do you actually stick these ultra-thin, super fragile chips together? Well, the old method, mass reflow, was kind of like putting the whole stack in an oven. Not great for thin chips, it could cause warping. Then you've got thermal compression, or TCB, which is way more precise, using localized heat and pressure. Even cooler is laser assist bonding, which uses a tiny laser to zap only the connection points. It's super fast. But really, the star for modern HBM is MR-MUF. It's a clever update on the old method that uses less heat and fills the gaps between the chips at the same time. It's fast, and it's perfect for this job.
So, after all that grinding and bonding and polishing and stacking, what does it all really add up to? And why is this process so important for, the future of everything? To give you a sense of the insane precision we're talking about, get ready for this number. Each single layer in an HBM stock has at least 1,024 of those tiny solder bumps that have to align perfectly with the layer below it. That's over 1,000 chances for something to go wrong, and it has to be flawless every time on every layer. So here's the bottom line. Every time you use a powerful AI tool or see a report about a new supercomputer, you're actually seeing the end result of this exact journey. It's this complex, beautiful dance of physics and chemistry that creates the high-speed engine that modern computing is built on. I mean, it's pretty wild when you think about it. We have literally conquered the third dimension in chipmaking, moving from flat planes to these towering skyscrapers of data. And it leaves you with this one last, fascinating question. As we push to stack 12 layers, 16 layers, maybe even more, how high can we actually go? What's the ultimate limit? Something to think about. Thanks for joining me.